Hi students, in this lecture I am going to discuss collisions. Let us see first the list of concepts. So first one, impulse. After that, types of collisions like one-dimensional collision or two-dimensional collision. Next, elastic or inelastic. And finally, variable mass system. Let us see first what is impulse. So impulse of a force is defined as impulse of a force acting on a particle is defined as integral f bar into dt. So from this we can say direction of impulse is direction of force, and we can say units from this. Units are force, that is Newton, time second, Newton second, or we can say kg meter per second, and we can say dimension formula kg, it is m meter, that is L, second power minus 1. So T power minus 1. That is now dimension formula. So impulse of a force acting on a particle is defined as integral F bar into dt. Direction of impulse is direction of force, right? So when we are focusing impulse, first we have to focus by which force. For example, consider a body on a surface which is a horizontal. See number of forces that are acting on the body. mg downwards, normal reaction upwards. Suppose applied force, it is F, frictional force, it is F. So now there are many forces are acting on the body. Now impulse due to applied force, or impulse due to normal reaction, or impulse due to gravitational force, or impulse due to friction. Like this, we have to mention by which force we want to calculate impulse. Okay. Suppose we are taking impulse due to all forces and taking the vector sum, then that gives us net impulse. So net impulse is given by, so either we have to calculate net force, then impulse of that net force. Otherwise, impulse due to each force, then taking the vector sum. So both are same, and that is given by, it is F net, impulse of net force, into dt. See from this what we get. According to Newton's second law, net force equal to rate of change of linear momentum with respect to time. So in the place of net force, I am writing dp bar by dt. It is dp bar by dt into dt. Then see what we get. It is equal to integral dp bar, which is equal to change in momentum. So net impulse on a particle is equal to the change in its momentum, which is known as impulse momentum theorem. I am repeating. Impulse of a net force acting on a particle is equal to the change in its momentum, and this is known as impulse momentum theorem. Okay. Right. And from this definition part, we can say one more point, that is, say we have learned that integration gives area, right? It is now integral f bar dt. Integral f bar dt. That means if we consider force time graph, if we consider force time graph, area under the graph with the time axis gives impulse of that force. For example, let us say force is given as F equal to 2t. Okay. So if I'm plotting a graph, it is now passing through origin. Graph is like this. This is now force and this is a time. Let us say we want to calculate now impulse by this force in the time interval t equal to 0 to t equal to 5 seconds. Then see what we get. So one is directly taking here integration, that is integral 2t dt. Then see what we get. So take 2 outside. T dt, t square by 2. Right now take limits 0 to 5, which gives it is a t square. It is a 5 square, 25. 25 Newton second. Now what I am saying here, integration gives area. So here if you take area under the graph with the time axis, that gives us impulse of that force. See here how much we get area. When I'm taking t equal to 5, force will be 10. 2 5 is 10, right? So 2 5 is 10. This is a 10. Then see area of this triangle. Area of the triangle equal to half base equal to 5, because we want to calculate from t equal to 0 to t equal to 5 seconds. So half base height equal to, height is now 10, right? It is a 10, which is equal to 25. Okay. So like this, area under the graph, area under the force time graph with the time axis gives impulse of that force. Or if we calculate impulse of net force, that will be equal to change in momentum of that particle. Okay. So like this, we can calculate the impulse. Let us see. So impulse momentum theorem, impulse of net force on a particle is equal to the change in its momentum. Okay. This is now what we have discussed. Let us see next one. Impulsive force. It is a large force acting on a body for a short time interval. While taking impulsive forces, other forces like gravitational forces are neglected. You can see, for example, a cricket ball is touching the cricket bat. You can see the time of contact is very small. In this short time interval, force by the bat on the ball is very large. So this is known as impulsive force because a large force acting in a short time interval. And while taking these large forces, remaining forces like gravitational force are neglected because those forces will be very small. So this is what we are going to use while solving problems. Let us see a problem. A block of mass m and a pan of equal mass. Block of mass m and a pan of equal mass are connected by a string going over a smooth light pulley as shown in figure. This is a block, mass is m, this is a pan. Its mass also m. These two are connected by a string going over a smooth light pulley. Initially, the system was at rest when a particle of mass m falls on the pan and sticks to it. Initially, this system was at rest because having equal masses, right? Now there is a particle of same mass which is a falling with a speed v on the pan and sticks to it. If the particle strikes the pan with a speed v, find the speed with which the system moves just after the collision. Let us see how to use now this impulse momentum theorem to solve this problem. Right. Let us make a diagram. So there is a pulley, block of mass m, and there is a pan, and a particle is moving down. See how many forces are acting on the block. So you can see one is a tension, which is always a pulling force, tension T. Its weight mg downwards. But remember, when this particle touches the pan, tension will be very large. That means tension is now impulsive force. Okay. So tension T, and here also tension is T. So when compared to this tension, its gravitational force mg is very small. So we are neglecting that. I'm repeating. When particle strikes the pan, tension becomes very large. You can see before the particle strikes the pan, tension was equal to mg, right? Tension mg, tension mg. But the moment it strikes the pan during that small time interval, this tension becomes very large. During that small time interval, this tension becomes very large. That means now tension is impulsive force. That's why we neglect gravitational force, mg, right? Let us now focus for this block. What is velocity? So for this block velocity, what I can do here, writing impulse momentum theorem, that is a net impulse equal to change in momentum of the particle. So coming to here, we are neglecting gravitational force. It is now only tension which is very large. Therefore, impulse due to tension, that is equal to, see carefully, now impulsive force becomes net force. Impulsive force becomes net force. And impulse of net force equal to change in momentum. So I can write this is equal to change in its momentum. Suppose a final velocity, take it as v dash. Final velocity v dash. And for the pan also velocity v dash. Therefore, final momentum m into v dash, initial value 0. So writing net impulse equal to change in momentum, right? Because tension is now net force. Right. Now coming to the pan. Coming to for the pan, see how many forces are acting. Coming to the pan, see number of forces that are acting. One is a tension, which is impulsive force, Now particle strikes the pan. So force by the particle on the pan, and that will be downwards. Let us take it as n. Now this n also very large. The tension very large, This force by the particle on the pan also very large. That means now we have to focus impulse due to tension, impulse due to normal reaction. Resultant of those two gives us net impulse on the pan. Let us take here sign convention because one is up and one is down. Let us take down as a positive. Then impulse due to normal reaction is positive. Impulse due to normal reaction positive. Impulse due to tension is negative. Minus impulse due to tension. This is now net impulse. This net impulse equal to change in its momentum. Initially for the pan, velocity was 0. Now velocity is v dash. So change in momentum is m v dash minus 0. Right? Now let us take one more equation for the particle. For the particle, the only force is now by the pan on the particle, that is n upwards. And we are neglecting gravitational force because normal reaction is now very large. Therefore, impulse due to normal reaction. And I am following again same sign convention down as positive. Since it is upwards, impulse due to normal reaction is negative. And this is now net impulse. And net impulse equal to change in its momentum. So finally velocity v dash, so it is m v dash, final value minus initial value, it is m into v, right? So we have taken momentum impulse theorem for the block, next for the pan, and next for the particle, right? Now you can see sum of these three equations. These two gets cancelled, these two gets cancelled. So left one, it is 0, 0 equal to mv dash, mv dash, mv dash. 3mv dash, okay, minus mv. That implies v dash equal to v by 3. So like this, we can use momentum impulse theorem while solving problems. Okay. Right. Let us see the next concept. Right. After impulse, it is now types of collisions. Okay. Let us focus now regarding collisions. See, when we are taking two bodies are colliding, let us take here two bodies. Suppose velocity u1 and mass is m1, and next one it is, this is velocity u2 and mass is m2. Let us take their velocities are along same line. Let us call it as x-axis. Their velocities are along same line. Let us call it as x-axis. You can see here, if you want to have collision in this diagram, condition is u1 should be greater than u2, right? Then only collision happens. Now you can see velocities along same line. After collision also velocities will be along same line. That means before collision and after collision velocities will be along same line. Then such type of collision is known as one-dimensional collision, or it is known as head-on collision. That means velocities before and after collision are along same line. Then collision is known as head-on collision, or it is one-dimensional collision. Okay. Suppose velocities are, let us take Let us consider a body having velocity in this way. Other body is now, let us take it is at rest. When this body collides with this one, you can see direction of this velocity vector after collision will change. So it will move now. This second body moves like this in this direction, and first body it may move like this. Velocity v1, this is u. Means after collision, their velocity vectors are in different directions. So such a collision is known as two-dimensional collision or oblique collision. So simply what we can say is, if velocities before collision and after collision are along same line, head-on collision, otherwise oblique collision. Okay. And here in this process, kinetic energy of the system before collision, or I can say just before collision and just after collision, if it is the same, that is known as elastic collision. For the system, kinetic energy just before and just after is the same. It is known as elastic collision. If it is not the same, known as inelastic collision. Okay, it is kinetic energy of the system just before collision and just after collision is the same, then it is known as elastic collision. Otherwise, it is inelastic collision. Right? Basing on kinetic energy, we can divide like this: elastic, inelastic. Basing on direction of velocities, it is one dimension or two dimension, or we are calling as a head-on collision or oblique collision. Okay. And here one important property is, if you take two colliding bodies, so before collision, there is velocity of approach. See carefully here. In this diagram, u1 must be greater than u2. That means this body is approaching the first body. There is velocity of approach. In the same way, after collision, there will be velocity of separation. There will be velocity of separation. If you take for this pair of bodies, the ratio, that is velocity of separation, I am taking modulus of that, 2 modulus of velocity of approach. So this ratio is a constant if you are taking the pair of colliding bodies. If you are taking the pair of colliding bodies, the ratio of modulus of velocity of separation to modulus of velocity of approach is a constant, and that constant is called as coefficient of restitution. So E is known as coefficient of restitution. It is known as coefficient of restitution. Means for the colliding bodies, modulus of velocity of separation to modulus of velocity of approach is a constant, and that constant is called as coefficient of restitution, and its value is 1. E value is 1 for elastic collision. For elastic collision, E value is 1. And if you take inelastic, its value will be greater than or equal to 0, less than 1. This is for inelastic collision. It is inelastic collision. If E value is 0, it is known as a perfectly inelastic. E equal to 0, known as perfectly perfectly inelastic. Okay, let us recollect once till now what we have discussed. So when you're taking two colliding bodies, velocities before and after collision along same line, known as head-on or one-dimensional collision. Otherwise, it is oblique collision. And next point is kinetic energy of the system just before collision and just after collision is the same. It is known as elastic collision, or otherwise it is known as inelastic collision. Okay. Now see carefully. Here one more point is like here force is acting on this one by this one. It is in this direction, right? Or let us take one more diagram. Let us see in which direction force acting on the bodies. Suppose one body is moving with a velocity. Direction is like this. Let us take other body is now at rest. Other body is at rest. You can see force by first body on second body will be along this line. Force by first body on second body is along this line. By second body on first body, force is along same line like this. This is known as common normal direction, in which along which line impulsive force is acting, because during collision the collision time is very small. In that small time interval large force is acting. Along which line this force is acting, that is known as common normal direction. Common normal. And if you imagine a line which is normal to that, imagine a line which is normal to that, that is known as a common tangential. So it is in along which line impulsive forces are acting, that is known as common normal, and normal to that it is known as a common tangential. Let us take one more example to get more clarity. Suppose consider we are projecting a ball from a height towards the ground. See here. Let us take this as a ground. A ball is now moving, making some angle to the normal like this. It is now moving, making some angle with the normal. Now force acting on the ball by the ground, it will be vertically upward. By the ground on the body, vertically upwards. This is known as a common normal direction because impulsive force is acting along this line. And if you take a horizontal, that is known as common tangential. Okay, let us take one more example. Let us take an inclined plane and we are dropping a ball from a height. When ball falls like this, force acts, force acts normal to the inclined plane. When ball touches the inclined plane, force acts normal to the inclined plane. So this is known as common normal direction. And if you take along the incline, that is known as a common tangential. So here we have to focus, one is a common normal, other one common tangential. How to identify means just focus along which line the impulsive forces are acting. That is known as a common normal direction. And normal to that, it is known as a common tangential. Okay. This is a way of identifying common normal and common tangential. And when we are taking only one dimensional collision, in that line, that line along which we are having these velocities is known as common normal direction. Means in one dimensional collision, velocities are along common normal. Okay. So when you are taking velocity of approach or velocity of separation, we focus along the common normal. That means this is taken as modulus of V2n minus V1n upon upon U2n minus U1n. So here we are taking velocity components along the common normal direction. Then we can calculate velocity of separation. We can calculate velocity of approach. Their modulus value ratio is a constant. Okay. This is what we are going to use while solving problems. Right.